Hello everyone, my name is Srihari Deshpande and today I will be presenting on nuclear magnetic resonance or NMR, which is a powerful analytical technique widely used across fields such as chemistry, biology and medicine. In this presentation, we will dive into the fundamental principles of NMR, its instrumentation, various techniques and applications and recent advancements. To start, NMR spectroscopy is a technique that exploits the magnetic properties of a certain atomic nuclei. It was first observed independently by physicists Felix Bloch and Edward Purcell in 1946, and they were awarded the Nobel Prize in Physics in 1952 for their groundbreaking discovery. Felix Bloch developed a technique to measure nuclear magnetic moments in liquids and solids, demonstrating how nuclei in a magnetic field could absorb and emit electromagnetic radiation at a specific resonance frequency. He introduced the concept of magnetic induction to measure the response of atomic nuclei to magnetic fields, which allowed the detection of NMR signal in bulk materials. Edward Purcell did the same for the paraffin. Today, NMR has become an essential tool in identifying and analyzing chemical structures due to its non-destructive nature and detailed information. It plays an integral role in molecular structure determination, particularly in organic chemistry as well as in the medical imaging known as MRI. Let's discuss the basic fundamental principle that make NMR possible. First, many atomic nuclei, like those of hydrogen and carbon, possesses a property known as nuclear spin. This means they behave like tiny magnets when placed in a strong external magnetic field. The magnetic moment or magnetic strength of those nuclei aligns with the field, creating a low energy state when aligned with the field and a high energy state when opposed. When we apply a radio frequency, that is RF pulse, at a specific frequency called the Larmor frequency, it causes the nuclei to flip from the lower energy state to higher energy state. This energy difference between the spin state gives us valuable information about environment of each nucleus, a concept known as resonance. The Larmor frequency is critical here as it directly proportional to the strength of external magnetic field. Additionally, the population of nuclei in each state follows Boltzmann distribution, with slightly more nuclei in the lower energy state. These differences in the population produces the NMR signal when the nuclei return to their original state. Now let's look at the main components in NMR instrumentation. First, we have a powerful superconducting magnet that creates a stable magnetic field necessary for NMR experiments. This magnetic field is essential as it aligns the nuclear spins in the sample. The RF transmitter generates and applies the RF pulses to the sample, while the receiver detects the signals emitted as the nuclei return to their equilibrium state. The sample is placed in a probe, which sits within the magnetic field. And finally, computers and software process this signal, converting them into the spectra through Fourier transform. Each component plays a crucial role in achieving accurate and reliable NMR results. Next, we will discuss several key NMR techniques. The most common is H1 NMR or proton NMR, where the hydrogen nucleus is analyzed. Hydrogen is abundant in organic molecules, making H1 NMR highly useful for studying chemical structure. 13C NMR, through less sensitive due to the lower natural abundance of carbon 13, provides valuable info on carbon framework. Beyond this, we have advanced techniques like two-dimensional NMR, including COSY, HSQC, and NOESY, which are useful for studying more complex structures. These techniques provide information on the connectivity between the atoms, aiding in the complete structural determination of complex molecules. Important feature of an NMR spectrum include the chemical shift, indicates the environment around each nucleus, coupling constant, which reveal interaction between nuclei and integration, which provides information about the number of equivalent nuclei. Now we will see the working principle of NMR. First, let's understand magnetic alignment. When nuclei with spin, like hydrogen or carbon 13, are placed in a strong magnetic field, they align with the field in a low energy state or against it in a high energy state. Next, we apply a radio frequency, that is RF pulse, that matches the energy gap between these two spin states. This causes the same nuclei to absorb the energy and flip to the higher energy state, and a process called resonance. After RF pulse stops, the nuclei relax back to their original low state and releasing the absorbed energy as they do so. This energy release is detected by the instrument as signal processing. The released energy forms a signal called the free induction decay or FID. This signal is captured and processed using a Fourier transform to create an NMR spectrum. Finally, we analyze the NMR spectrum. Features like chemical shift, coupling constant, and peak intensities in the spectrum reveal detailed information about the molecular structure. Now, the NMR measures the resonance frequencies of atomic nuclei in a sample, typically hydrogen or carbon atoms. It represents the frequencies reflects the chemical environment around the nuclei, revealing details about the molecular structure, bonding, and dynamics. The results are plotted as an NMR spectrum where the x-axis shows the chemical shift in parts per million, representing the resonance frequencies, and the y-axis indicates the signal intensity, which correlates with the number of nuclei in each environment. Peaks on the spectrum correspond to the different chemical environments in the molecule. This is the sample graph of NMR, the proton NMR spectrum of butanol 1. Here are some key features of NMR, which is our chemical shift, coupling constant, integration, and multiplicity. NMR has extensive application in various fields. In chemistry, it is used to determine molecular structure. By analyzing the unique chemical shift values and coupling patterns, chemists can identify functional groups and establish molecular connectivity. In biology, NMR is applied to study biomolecules like proteins and DNA. High resolution NMR techniques are used to analyze their structure and dynamics, which is crucial in understanding biological processes. The pharmaceutical industry uses NMR for drug discovery, structural analysis, quality control. NMR's role in medicine, particularly in MRI, is widely known, where it allows non-invasive imaging of tissues based on hydrogen atoms in water molecules. This application is indispensable in diagnostic. Let's touch on some recent advances. Cryogenically cooled probes, for instance, improve sensitivity by reducing. Now, these are some advantages and limitations of NMR. Now let's touch some recent advances. Cryogenically cooled probes, for instance, improve sensitivity by reducing thermal noise, allowing for better signal detection. High resolution magic angle spinning, that is HRMS, is another advancement used in solid state NMR for improved resolution. Another fascinating field is metabolomics, where NMR is used to analyze metabolic profiles in cells. This approach has application in disease research and diagnostic, offering insights into the molecular composition of biological samples. In summary, we have explored the basics of NMR, its instrumentation, various spectroscopy techniques, and vast range of application across fields. While there are so many limitations, ongoing advancements continues to enhance NMR capabilities, expanding its use in research, industry, and medicine. Thank you so much for listening to me.